Okay, so let's look at the next equation, the ideal gas equation. Now this is crucial to understand this. We are assuming that the gas will react as the ideal gas. It would be the perfect gas, based on the principles that we've discussed in the previous video about which properties an ideal gas will have. But we can basically with very high accuracy do calculations of this equation, except where there is deviations, where there are deviations which should be at a very low temperature, for instance, which we'll talk about just in a bit. But for now, let's just focus on the calculations. The previous video referred to the general gas equation. So it was when you had a scenario with known temperature, pressure, and volume, and you changed those properties, and then you had to calculate the new unknown. Let's say, for instance, you change pressure and temperature, what's the new volume? Or you change pressure and volume, what's the new temperature? So that's when you have two different scenarios. With the ideal gas equation, it is different. You do not have two different scenarios. You have a single scenario with one unknown. Okay, so for instance, and let me write down the equation for you that will help you. PV equals nRT, where P is your pressure, and the pressure has to be in Pascal. And this is SI units, okay? The volume, V, has to be in cubic meters. Again, SI units. All of these will be SI units. The N is the amount of mole, and it has to be in mole. And then temperature has to be in Kelvin. Now, the value R is a constant, okay? And this constant will always be given when you do your calculations. And this constant is 8,32. It's technically 8,314, but we are going to work with 8,32, and this unit is joule per Kelvin per mole. And that unit, that constant will be given. Okay, so this is the ideal gas equation. Again, you will have, let's say, the pressure, the volume, and the temperature, and then they'll ask you how many moles were there in the container. Or you would have the moles, the temperature, and the volume, then they'll ask you what will the pressure be in the container. This is typically how these questions will look like. Okay, so we will do an example just now. And this example is taken from the Study and Master textbook, grade 11, Physical Sciences, and it's on page 172 if you want to do your own referencing. Okay. So it asks you to calculate the temperature in degrees Celsius. Very important, that will come into play at our final answer, of 5 moles of oxygen gas kept in a 300 cubic decimeter container at a pressure of 75 kilopascal. Okay, so first things first, let's write down the information that we have. Okay, so they want temperature. So I'm going to put that down as an unknown. The amount of moles is 5. And we know it's oxygen gas, so it's O2. Then they told us that the volume is 300 cubic decimeters, and the pressure is 75 kilopascal. Okay, your first step always with the ideal gas equation is convert into the correct units. Okay, so 300 cubic decimeters. We know there's 10 decimeters per meter. That means there's 1,000 cubic decimeters per cubic meter. So this is 0,3 cubic meters. The pressure was easier to convert. You just had to multiply with 1,000 to go from kilopascal to pascal. So that is 75,000 pascal. And the temperature is unknown, 5 moles already in SI units. Okay, now let's apply. PV equals nRT, and we want to calculate temperature. Let's just substitute. So 75,000 times 0.3 equals 5 times 8,32 times temperature. Again, I'm just showing you this step for the sake of our calculation. 75,000 times 0.3 divided by 5 and 8,32. And now let's do our calculation. Let's see what's the answer. So temperature is equal to 542 Kelvin. And remember, the question stated that we need to give our answer in degrees Celsius. So therefore we know it will be 542 minus 273, which will give us an answer of 269 degrees Celsius. And this is how you apply the ideal gas equation. Please refer to page 173 in the Study and Master textbook to go through the deviations from the ideal gas equation. And for that first graph on page 173, have a look at how normal gases react at low pressure and high pressure versus the ideal gas. So have a look at that. And then also the next graph, look how real gases react at low volume versus high volume. Like meaning low temperature, high temperature, and what happens to their volumes. So just have a look at when and how it deviates from the ideal gas.